Hi all, welcome back to Cracking the FANG interviews. Today we're going to be talking about a very important problem, which is searching in a sorted rotated array. And this problem has been asked at Microsoft, Google, Netflix, and among other top FANG companies. So let's just look at what's given to us in this problem before we think about a solution. This is clearly a search problem. We are looking for some element given to us, which would be x, and we are also given sorted array here. So the first thing that comes to my mind is a linear search, and maybe we can think about doing better than that later. But let's look at the problem in more detail from here. So here is a snippet from the Leetcode page for the problem. We are given an array called nums, and we are supposed to return an index k within this array, which has the target element we are looking for. So in this particular example, this is the sorted rotated array. The array starts from 0, goes to 1, 2, and then loops back on the other side. So that is what we mean by a rotated array. Let's look at another example. We have this array which is 0, 1, 2, and then it loops back on the other side, and we have 4, 5, 6, 7. So what we are looking for here is an element in this array, in both these arrays. So let's look at it. We've been given a target value of 0, so 0 is here. The program is going to expect us to return the index, which is 4 in this case. And in this array, we are looking for number 3. 3 is not present in the array, so we'll be returning -1. So let's look at an example. If we are given a sorted rotated array, and I'll start up with a very simple example of 3 elements. So we have 3, 1, and 2. This is a sorted rotated array. The elements are in increasing order, but it has a cycle or a rotation. Again, indexes for the array. If we were to be looking for an element in the array, for example 2, the first solution that comes to my mind is brute force. And what we do here is we linearly scan through each element in the array, and if we find the element, we just simply return the index. The time complexity of this solution is going to be O of n, since you're linearly going through the entire array, and in the worst case the element is going to be at the last position. So that's what gives you the linear time complexity. Now the natural question in most of coding problems is, can we do better? And we are given this property of sorted arrays, right? The array that is given to us is sorted and rotated. So let's assume if it were to be only be a sorted array. We know this algorithm which could efficiently search a sorted array, which is binary search. And what binary search essentially does, to quickly touch upon the idea, is since it only operates on sorted arrays, and what it does is it looks at the middle element, and it clearly knows if the element you're looking for is on the left side or on the right side, and it splits the search space by half every time you go through the array. So if you have an array of size n, you'd split it into n by 2, n by 4, and so on until you reach the size of a single element. And the time complexity of binary search, as we know, is O of log n, since it's splitting the search space by half. But here we have a sorted rotated array. So the question is, can we apply this concept of binary search to a sorted rotated array? And the answer is yes, we can do that. So the array is still sorted. If you were looking for an element 2, let's just apply plain binary search, and we'll try to modify it as we go along. And if you're looking for this element 2, the first thing we do in binary search is we find the mid index. We'd be at 1. What we do here is, instead of directly sort of using the sorted property, we'll try to understand which side of the array is sorted. So step one is find sorted side. So what I mean by that with a concrete example is, since this is my bit index, I check if this the right side is sorted or is the left side sorted. In this case, I can clearly tell that my right side is sorted. And if you know your right side is sorted, you can check if your element lies within the right side by just comparing the start and end values within the array. So if I'm looking for 2, I clearly know 2 is within this side, and I can move my start pointer, which was originally here, to the other side and search within this space now, which is 1 and 2. My start pointer would be at index 1, end pointer would be at index 2, and I'd eventually come to 2. So if the idea is clear, what we are trying to do here is first find the sorted side. Step 2 would be go search through the sorted side. Like we do in plain old binary search. Now, there is a corner case to this. There could be a case where the pivot is not where your mid is, and you might not know which side is sorted. So what do we do in that case? Let's look at a few examples and make the idea more clear and concrete. So I'll jump into the code and try to address that as I walk through that corner case. But the overall idea will remain pretty much the same. We are looking for the sorted side. Depending on the sorted side, we know if the element is within that sorted side. If not, we go to the other side, which can still be unsorted, and we'll handle that later. So again, whenever I I need to use binary search, I prefer a iterative implementation. The reason for that is recursive implementations are a little more complicated to visualize and understand, and they could lead to infinite recursive stacks. And in production code, you should always prefer iterative algorithms as a thumb rule. And here I've been given an input array nums. I start with start and end index for the array nums, and I have my target as we discussed earlier. The first thing we do is we calculate the mid index, which is start plus end and divided by 2. So it gets you to the middle of the array, as we saw earlier. And if the element we are at is the target, we return right there. Same as binary search. I haven't made any changes to binary search still here. And let's look at the next step, where we are looking for the sorted side. What we could do is look at the right side, say, is this side sorted? What does it mean to be sorted? It means you have elements in increasing order, 1, 2, 3 as an example, or you could also have elements which are exactly equal. So for example, 2, 2, 2, even though they are not in increasing order, the array is still sorted. So that is what gets the less than equals to sign. And once you know this side is sorted, what you could do is compare if your target is within the sorted side. If it is, you go and search within sorted side. And if not, you'd simply go to the other side, like in plain old binary search. I also have this else case which says, if my right side is not sorted, then you go and check if the target is within the left side, and I can quickly visualize that. We essentially go and check the left side here, and if it is, you move your end pointer from the right end onto mid -1. You've clearly checked mid already, so you don't need to be double checking there. You'll make this as your search space and divide it by approximately half, as you do in binary search. If not, you're gonna move your start pointer by mid +1. So the start pointer would move, and this would be your search space. Again, it's almost n by 2, as you can see, and we keep doing that till we reach one element, or we've already found our element at mid. So the whole idea is a sorted array, given to you as a quick recap, could be 3, 5, and 9. And if you're looking for an element 5 within this array, you can sort of get get a quick hint on the directionality if 5 could even be present by just looking at the first and last element within the array, since the array is sorted. I hope the idea was clear. Thank you for watching this video from Cracking the Fang Interviews, and please like, share, and subscribe for more exclusive